The F-35 Lightning II is more than a fighter jet. It's the world's most advanced multi-role stealth aircraft, a flying supercomputer, and one of the most expensive weapons programs in history. But behind its advanced design lies an engineering paradox. How do you make an aircraft nearly invisible to radar, powerful enough to give pilots the edge in dogfights, and still capable of launching precision strikes from sea or land? Every breakthrough comes with trade-offs. Radar-absorbing stealth coatings that require constant maintenance, engines that reach turbine temperatures of over 3,400 degrees Fahrenheit in afterburner, and software so complex it can ground the entire fleet. Today we're breaking down the engineering of the F-35. Stealth, propulsion, avionics, materials, and cost, to uncover why this aircraft is both a marvel of technology and one of the Pentagon's most debated creations. There are 3 variants of the F-35, each engineered for a different mission environment. The F-35A is the standard Air Force model, designed for conventional runways. The F-35B is the short takeoff and vertical landing version, using a Rolls-Royce lift fan and swiveling exhaust nozzle to operate from short decks and amphibious assault ships. And the F-35C is the carrier variant, with larger wings, folding tips, reinforced landing gear, and a tailhook to survive the brutal stress of catapult launches and arrested landings. These unique adaptations forced engineers to balance weight distribution, lift, and engine performance differently in each version, proving that stealth wasn't a one-size-fits-all solution, but a flexible design philosophy stretched across 3 very different aircraft. At the heart of the F-35 is the Pratt Whitney F135, the most powerful engine ever fitted to a single-engine fighter, generating about 28,000 pounds of dry thrust and nearly 43,000 with afterburner. It propels the jet beyond Mach 1.6 and nearly 50,000 feet. Air is compressed through multiple fan and turbine stages, ignited in the combustor, and expelled at supersonic speed through a stealth-shaped nozzle, turning raw airflow into controlled, lethal thrust. For comparison, the twin engines of the F-22 Raptor produce about 70,000 pounds combined, showing how remarkable the F-135 is for a single-engine platform. But power alone isn't enough. Unlike Cold War jets that chased raw speed, the F-135 was tuned for survivability and low observability. Combustion dynamics, turbine stages, and nozzle geometry are optimized to run hot and efficient, while minimizing signatures that could reveal the aircraft. Afterburners deliver augmented thrust for rapid acceleration, but engineers carefully manage the exhaust with cooling, nozzle shaping, and heat-resistant coatings. Advanced thermal management systems mix and cool hot gases to lower infrared visibility, while stealth nozzle designs reduce radar reflections, allowing the F-35 to sprint when needed without compromising its low observable profile. For the F-35B, things get trickier. The lift fan and swiveling rear nozzle redirect thrust vertically, demanding a radical redesign of exhaust flow and heat shielding to make vertical landings possible. The F-35's most defining feature is stealth. Its fuselage is shaped to scatter radar waves, while radar-absorbing coatings soak up energy to reduce detectability. Internal weapons bays eliminate external hardpoints that would raise its radar cross-section, and even seams and fasteners are carefully aligned to minimize reflections. Beneath the surface, advanced composites make up nearly 40% of the airframe. The wings and much of the structure rely on carbon fiber reinforced polymers for strength without weight. Around the engine and high heat areas, bismulimide resins keep their form under extreme temperatures. And on the outer skin, radar-absorbing composite panels are built directly into the fuselage to dampen enemy tracking. These materials endure supersonic stresses, resist thermal extremes, and cut down on corrosion. But the precision needed for their manufacturing and upkeep makes them one of the program's costliest requirements. It is often called a flying computer, because software and data, not just engines and missiles, define its edge. With over 8 million lines of code, more than most commercial airliners and even some space programs combined, it runs one of the most advanced avionics systems ever built. Its sensor fusion integrates radar, infrared, and electronic warfare inputs into a single, intuitive display projected inside the pilot's helmet visor. This helmet doesn't just show numbers and targets. It lets pilots literally see through the jet, with a 360-degree view from the distributed aperture system. For the first time, a fighter doesn't just provide information, it provides understanding. In combat, that clarity can mean the difference between victory and survival. And the F-35 doesn't fight alone. Acting like a digital quarterback, it networks with other aircraft, drones, ships, and ground forces in real time. In modern warfare, information isn't just power, it's dominance. And the F-35 delivers it at supersonic speed. The F-35 was built as a multi-role stealth fighter, one jet capable of air superiority, precision strikes, and electronic warfare. But merging these roles forced engineers to solve three impossible equations. First, power without compromising survivability. The F-135 engine delivers enormous thrust, but its thermal and radar signatures had to be tamed to keep the aircraft stealthy. Second, maneuverability without sacrificing stealth. The airframe needed agility in combat while preserving radar-evading shapes and coatings. And third, advanced avionics without overwhelming the pilot. Millions of lines of software code that filter and fuse data, so the jet enhances human decision-making instead of drowning it in information. Every curve of the airframe, every material, and every line of code was shaped for one goal: to survive and strike in contested environments where staying hidden is as vital as hitting first. Every system reflects compromise. Stealth reduces maneuverability. Internal bays limit weapons load. Engine heat threatens infrared concealment. Materials must withstand supersonic airflow yet remain maintainable. These competing requirements were balanced to create a platform effective across missions, while never excelling at only one dimension. The F-35's design has already been tested in combat environments and multinational exercises. Its stealth allows it to slip through radar networks, while its sensors and weapons deliver precision. Engineers built it to stay operational across extreme conditions: desert heat, maritime humidity, even Arctic cold, proving its adaptability in real missions worldwide. The F-35 program has cost over $400 billion to develop, with projected lifetime expenses above $1.7 trillion. Unit prices have fallen to about $90 to $100 million per jet, though its helmet-mounted display system alone costs around $400,000 per pilot. Critics cite software delays, sustainment costs, and maintenance burdens. Supporters argue its stealth, avionics, and versatility justify the expense. This debate remains unresolved, fueled by the sheer scale of the investment. The F-35 Lightning II is both an aerospace marvel and a cautionary tale. Engineering genius pushed it to the limits of stealth, propulsion, and digital warfare, yet compromises and costs make it one of the most debated aircraft in history. So what do you think? Is the F-35 a triumph of modern engineering, or an example of over-engineering? Share your perspective in the comments below. And if you enjoyed this deep dive, don't forget to like and subscribe for more breakdowns of the world's most ambitious engineering projects.